Morning, Leipa.
Good morning.
Looks like you're first to join.
It's because I put an alarm for the morning and I woke up. So I've been up since then.
Oh, yeah. We're going to go through the end of chapter questions that he posted.
From the textbook.
Yeah,
Yeah.
yeah. Let's just go through all of them one by one. All right, it's probably best if we get started, and if people join late, they always have to record them.
No problem.
All right. All right. Good morning, everybody. Today is part 2 of a review, final review. And today my strategy is just to go over all of the complete set of end of chapter questions that the professor has posted. Can you hear me okay, Leba?
It's actually a little bit muffled. Like I have you
It
on
is.
full volume, and it's
Got it. Thanks for letting me know. Let me try let you get much of, and then tell me if this makes it better, okay?
Mm-hmm.
Okay,
So let's review.
let's see. Is this better?
Way better.
We're almost done and then you can go on. The sauce on the list of words that are okay.
Is this any better?
Yeah, it's way better.
Oh, hold on. Oh, I got it. Give me 1 second. Let me fix this.
Yes, the situation is suspicious. So, well, you can listen. Listen, guys. We're almost done. So it's a one, we want to 2, and I'll ask the other stuff. 2, you can send it to me. He wants. listen to everything you want, you're not slow on it. And it takes it inside his mind. Those are things that build up, you guys are clearing the way. And then in terms of like, where you can say cells, but now like one that are on there. So it's say, same with the
Someone said they're waiting in the waiting room.
All right. Let's see. 1 second.
Almost done, and then for a playground time, this is the last one.
Okay, I can hear you guys now. Can you hear me well now? Say that again.
Whatever we decide. Would you like to say?
Well, because I'm using a microphone now, you'll have to put your questions in the chat. I won't be able to hear you. Just by putting in the chat, can you hear me okay? Do I sound fine? Yeah? All right. Cool. Get started. All right, let me do this again. Part 2 of final review today and go over the complete set of end of chapter questions that the professor has. Okay, let's just run through them one by one. First question, chapter 10. Question 21A. Identify the intermolecular forces. I'm not sharing my screen, I'm on it. Identify the intermolecular forces present in the following solids. And we are to look at part A. It's okay, we can look at all three of them. If you look at part A, it has an OH in it, which is indicative of a hydrogen bond. And so because it has hydrogen bonding, remember, it must also have dipole-dipole. And everything has them. So those are the three intermolecular forces present in 21A. 21B, on the other hand, is a hydrocarbon. All I see are carbons and hydrogens. And if you remember, hydrocarbons are non-polar. So the only forces present on the London dispersion forces. 21C has a chlorine in it, which makes it polar. So there is dipole-dipole. salt, but there is no oxygen, no hydrogen, so there is no hydrogen. Those are all the molecular forces. Next question. 43A. It takes longer to cook an egg in Fort Davis, Texas, altitude 5,000 feet above sea level, than it does in Boston, which is at sea level. That's maybe the observation. So let's see. As you go up to higher and higher altitudes, the pressure decreases. Water boils when the vapor pressure is equal to the atmospheric pressure. Water boils when the vapor pressure becomes equal to the ambient atmospheric pressure. So if the atmospheric pressure is lower, then that means that the vapor pressure needs to be lower before water can start boiling. Which means that as you go higher and higher in altitude, the pressure decreases. And so the temperature at which water boils also decreases. Which means that at higher altitudes, water boils at a lower temperature. Making the food take longer to cook. And that is the explanation. 43B. Perspiring is a mechanism for cooling the body. Perspiration is evaporation of sweat, which is mostly water. Evaporation of water is an endothermic process. It takes heat, and that heat required to evaporate the sweat from your body is taken from your body. So as the sweat evaporates and leaves your body, it also captures some of the heat from your body and dies. So that's 43B. Question 55. What phase change will take place when water is subject to varying pressure at a constant temperature of 0.005 degrees Celsius, at 40 degrees Celsius, and at negative 40 degrees Celsius? Take a look at this figure. Okay, this is the phase diagram of water. 0.05 is all the way down here somewhere. And as you, oh, sorry. What was the, but basically they gave you a certain temperature. See, for example, you look at 40 degrees, which is somewhere over here, and you change the pressure. So you move the pressure is the y-axis. So you're going from gas, and you cross paths down to liquid. Gas to liquid, that is condensation. Right, so let's recall phase changes. Ice to water is melting. And the reverse, water to ice is freezing. Water, liquid to gas is evaporation or vaporization. Gas back to liquid is condensation. Solid directly to gas is sublimation. Gas back to solid is deposition. That's the weird deposition. And so you look at 40 degrees and you cross pressure, go up or down and see what two values are. At a temperature of 0.05, which was somewhere really down here, you see that you go from gas directly to solid, which is sublimate deposition. So look at your appropriate temperature and then cross the cross up and down to see what phase change happens. On the other hand, if they told you pressure information, like for example, tell me what happens as you cross temperatures at 101 kilopascal of pressure. You stick yourself to 101 and then you move left or right to change that. You see that by the first, you cross the ice water, a solid liquid barrier, so that's melting. And then you cross from liquid to gas, which is freezing. Exercises. Just remember for anyone who's just joined, I can't hear you, but I can read your chat. Because I'm using this mic. All right. Question 69. Identify the type of crystalline solid formed by each of the following substances: metallic, network covalent, ionic, or molecular. Metals with non-metals form covalent ionic bonds. So take any of the first two components of the periodic table, first two groups, versus any of the second half of the main group. If you have any combination like that, that's ionic combination. So they will form ionic crystals. Calcium chloride, metal with the non-metal. So it's definitely an ionic. Next up, silicon carbide, both non-metals, and they're held together by silicon carbide. It's a network covalent compound. No. Silicon carbide is a molecular substance. That's because if you look at the lattice structure of silicon carbide, not everything is joined to each other. You have molecules of silicon and carbon. So you have silicon and carbon that are joined to each other. Oh, are they also joined to each other? Oh, okay. Never mind. Yes. Okay, so every molecule of silicon and carbon is joined to every other molecule of silicon and carbon. So it's all interconnected. Here's the difference between molecular compounds and covalent network compounds. In covalent compounds, you have these covalently held molecules, but the molecules themselves aren't interconnected. One molecule is not connected to the other molecule. There are weak intermolecular forces, dispersion or hydrogen bonding, dipole, something like that. But there is nothing actually connecting this. There's no covalent bonds connecting the two. Network covalent bonds are where all the molecules are connected to all the other molecules via covalence, as you can see here. All of these solid lines are covalent bonds, and you can see going from one to the next, you have a big covalent bond. Going from one to the next, there's a big covalent bond. Silicon carbide is an example of a network covalent solid. Copper is just a metal. Pure metals are metallic crystalline solids. That's self-explanatory, right? If you have metal all by itself, then it's just metallic. Carbon dioxide, on the other hand, is an example of a molecular crystalline solid, because carbon dioxide is a molecule covalently held, but the molecules of carbon dioxide are not covalently bonded to each other. That's a molecular crystalline solid. Carbon is an example of a network covalent solid, because each carbon atom is connected to its neighboring carbon atom via covalence. Barium sulfate, as you can guess, it has a metal in it and a bunch of polyatomic ions, which consists of nonmetals, so that's an ionic compound. NH3 is I don't think NH3 is a solid. It's a gas, but I guess if you cool it down, then it becomes a molecular solid. And so on. So NH4F, even though it has all non-metals, it is an ionic compound because NH4 is a polyatomic ion. The presence of a polyatomic ion tells you that the compound is ion. NH4F is an ionic group. But still is not actually NH4F will form an ionic crystal solvent. That much is true. Yeah. So anything that's ionic has anything that has at least one ionic bond in it will form an ionic crystal solvent. Cool. Like I said, put your questions in the chat if you have any. So we're done with chapter 10. Review, ask for the professor. Moving on to chapter 11. 11, question 24. I'm going a little fast today because we have a lot of questions to cover, and also because we have access to the recording. Henry's law constant is given, assuming an ideal solution behavior with pressure on carbon dioxide is needed to maintain a CO2 concentration of 10 molar and lemon lime soda. Henry's law is given by C equals KE. So this is a simple solve for C kind of question. Henry's law, and for Henry's law equation. What is this question? We're given that K, Henry's law constant, is KH. 3.4 times 10 to the negative 2. For atmosphere, Henry's law equation is K, KH, E, and we want to calculate the concentration. That is going to be 3.4 times 10 to the negative 2 per atmosphere. Max pressure, you want to maintain a pressure of, oh no, you want to maintain a concentration of 0.10. So we are solving for pressure. All good. Concentration is 0.10. Solve for P. Divide both sides by 3.4. Times 2 to the negative 2. This is molars per, this is molars. And this is molars per atmosphere. The molars cancel and the surviving unit in atmosphere. They both plug and chug into Henry's law. It's question 3 of chapter 3. Next, 31b. What are the mole fractions of HN3 in a concentrated solution of nitric acid? Okay, this is question 31b. HN3 in water. And mass percentage 68%. HN3, what kind of a percentage is this by mass? Percentage questions, we start with 100 since it's mass in grams. So out of 100 grams, 68 grams is HN3. So the rest is water, 68, 32. Want to calculate mole fraction. So we have two mole fractions here, mole fraction of HN3 and a mole fraction of Mole fraction, remember, is mole of one thing divided by total moles. So let's get the moles of each of these guys first. 68 divided by mole of math of 8. $63 and 32 divided by 8. That gives us the number of moles of each of these. Let's say this comes out to 1, this comes out to 2. So the moles of HNO3 will be the number of moles of HNO3, which is the first number, divided by the total number of moles. That plus that. Similarly, this is second number, moles of H2O divided by total. Intertime. That's more right. Very simple application of the more practical. Next up, 39B. Calculate the molality of the following solution. 125 grams in each one of 3. 30. $275 grams of water. One is right. Recall molality is little m given by moles of solute divided by a kilogram of solvent. Okay, so little m is going to be, let's take 125 grams of our solute and convert it to the moles out of it divided by the mass. Just 80. So that gives you a number. Molality is that number divided by kilograms of solvent, which is 275 converted to kilograms. You do number 6 on the final exam practice question. Oh, it's hard to hear me? That I'm telling me that was important. Tell me if now is better. Okay, cool. Better now. Can you do number 6 on the final exam practice problems? Number 6. So number 6 from what I am going through right now. Or the practice exams that he posted. A practice final exam. Let me take a look. Was it? And it's not the thing that I covered in review 1. Is that the same as review 1 or? Yes, I already did. So review 1, yes. Yeah, look at the recording. Review 1 is all about final exam practice problems. Yeah, I went through all. Yeah. Cool. This guy, yeah, the molality, get your moles, divided by kilograms of solvent, which is 285, 39B. Okay. Next, 43B. Assuming ideal solution behavior, what is the boiling point of a solution of 115 grams of non-volatile soup in 350 grams of water. Boiling point, and I see solvent and solute, so this is colligated property. Will be 3B. Got 115 grams sucrose and 350 grams of water. What do we want the boiling point. K delta TV equals I times KB times M, colligated property boiling point change equation. Delta, remember, stands for solution minus pure, solution boiling point minus solvent, boiling point or pure boiling point. Equals I times KB times M. We want to solve for the solution temperature. And so that's just going to be temperature of pure water or boiling plus I times KB. M, pure water boils 100 degrees Celsius. I is 1 because this doesn't break up into pieces. It's a covalent compound. KB is given, not given. You want to rise KB. KB is 0.512. Times molality. So that's something we need to figure out. Just like 39B, that's how you figure out molality here. Take your 115 divided by the molar mass of sucrose, which is, let's see, sucrose. 342. That gives you the number of moles of sucrose, and then divide that by kilograms of water, which is 0.35. That goes there. You're done. Very simple boiling point colligated property question. Next, chapter 12. These problems are easy. I don't know why he is giving you easy problems for review. Chapter 12, question 3. The nuclear industry, chlorine trichloride is used to prepare uranium hexafluoride, volatile compound of uranium used in the separation of uranium isotope. Chlorine trichloride is prepared by this reaction. Write the equation that relates the rate expression of this reaction to the disappearance of CO2 and formation of the electron. Okay, it's a common step. Chapter 12, question 3. Can you hear me okay? Cl2 plus 3F2 gives 2ClF3. So the rate of the reaction, remember, given by reactants get negative, products get positive. Negative ddt. So the rate of change, the concentration of CO2. Chlorine. So reactants get negatives, products get positive, and you divide out the coefficient. So for Cl2, that's what it is. For F2, there's a coefficient of 3, so let's divide that out. It's a reactant, let's put a negative. Rate of concentration change of F2 over with respect to time. Here, there's a coefficient of 2 divided out, and its products to make it positive, ddt of ClF3. This here is the rate of disappearance of Cl2. This here is the rate of disappearance of F2. This here is the rate of appearance of ClF3. And this is how they're related to the rate of the reaction. Next, question 15. How will the rate of reaction change by the process, blah, 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 if the rate law for the reaction is, let's see, rate of the reaction. Question. If the rate of the reaction is K NO2 to the power of 2. Decreasing the pressure from 0.5 atm, so NO2, want to take it from 0.50 to 0.25 atm, which is halving the pressure. So you took the amount of NO2 and you reduced it in half. So that's going down by a factor of 2. Right? Changed by a factor of half or decreased by a factor of 2. NO2 is related by a square, right? So the rate of the reaction is going to go down by a factor of 2 squared, which is going down by a factor. The rate of the reaction will become a quarter of the original. It's going to go down by a factor. It's going to get divided by. Next one, increasing the concentration of CO from 0.01 to 0.03. The next piece of information is given about CO, but CO does not appear in the rate law. So CO will have no effect. Hypothetically, imagine that the rate law was given to be K NO2, and CO. And the question said, let's say that NO2 went up by a factor of 2, and CO went down by a factor of 3. Went up by a factor of 2 means 2 times. Went down by a factor of 3 means a 1/3 time. That's another way to look at this. Which means NO2 has a squared, CO has just a single power. So the overall effect on the rate of the reaction is going to be 2 to the power of 2 times 1/3 to the power of 1. You take the change and then apply the power for each species. So that gives you 4/3. Question 27. Because people see. And you're given some data. It's okay. There's only one reactant. How do you write rate laws? K times concentration of the reactants to some. That's all we use any one rate law. You actually use 2 rate laws. Let's see, 4.17 times 10 to the number 4. This K concentration of A here is 0.230 to the power of n divided by, take any other one, 9.99 times 10 to the power of 4 equals K times 0.356 to the power of n. The K's cancel, these cancel, combine the power. 0.230 divided by 0.356 to the power of m equals 4.17 over 9.99. Solve for m, you know how to do it. We did a very similar question in review 1, and then come back and solve. We've done this before. Question 38, on the other hand, is what is the half-life of decomposition of NaCl when the concentration of NaCl is 0.15? Don't go ahead and immediately use the ln2 over k, because that only applies to first order reactions. This is a second order, so we'll have to do something different this time. Okay, let's look at this, question 38. What is the concentration of NaCl? What is the half-life for the decomposition of NaCl with the initial concentration is 0.15? Okay. NaCl is 0.15. This is initial. And so since you're looking for half-life, you want this to be reduced to half, which is 0.075, I believe. And its a K value is 8 times 10 to the negative. Great. Recall the second order kinetics equations. Yes. 1 over A equals K here plus 1 over A naught. 1 over A is 1 over 0.075 equals K, 8 times 10 to the negative 8 times T plus 1 over A naught to the 15. Solve 15, you're done. That's all it is. The trick in this question is to realize that we can't use T hat equals K over ln2 over K, and that only applies to first order, second order. Okay, moving along. Question 38. 62. Okay, you're given a bunch of different temperatures and a bunch of different K values, and you want to calculate what the activation energy is. This is where the activation energy formula comes in. Arrhenius equation. Just get rid of I. Arrhenius equation relates K to temperature. And also activation energy is part of the given by given by K equals, there's a bunch of different variations on this, but I'm going to use this one. K equals A e to the minus EA. We have two different K values. We have a bunch of different K values at various different temperatures. Let's pick two different temperatures and two different K values. So let's say 555, 575. Corresponding to different orders. That should be good enough. So let's call the first K value K1, which happens to be T1, K2, which happens in temperature T2. So we've got K1 equals A e to the minus EA over RT1. The activation energy remains constant if there's a change in temperature. R is a constant, A is a constant. K2 is A e to the minus EA over RT2. Divide the two equations to get rid of this A that is necessary. We don't need it. And so K1 over K2 equals E to the minus EA over RT1. And if I bring this here, it becomes time E to the EA over RT2. Which makes the right hand side simplified to A to the M times A to the N is A to the M plus N, right? So this becomes E to the negative EA over RT1 plus EA over RT2, which is the same as saying you know what? Just use this variation of Arrhenius equations to do all this, which goes ln K1 over K2 equals EA over R negative 1 over T1. You have your K1, you have your K2, you have your two temperatures. This is an activation energy, so this is an energy question. 8.34. Solve for it. What's it? Simple as that. Okay, next up. Right rate law or 72B. Okay, that should be pretty simple. Specifically 72B. And O3 plus Cl gives O2 plus Cl. LO. And the question specifies that this is an elementary reaction. What's special about elementary reactions? Coefficients are the powers. Usually we have some unknown m and some unknown n as the powers. Here the coefficients are themselves the powers. That's special about elementary reaction. The rate law is going to be given by rate equals K times concentration of the first reactant O3, concentration of the second reactant Cl, and instead of the m and the n that we have usually, it's just going to be the coefficient of O3, which is 1, the coefficient of Cl, which is also done. The coefficient of O3 was 2 to the power of O3. Okay, along question 13, chapter 13. Spend more time on this. 15 B and H. Chapter 15. 15. Yeah, B and H. I'm gonna do H. Yeah. Do H. 15. Sulfate dot 5H2 solid. Equilibrium type. Copper sulfate also solid. Plus 5H2O gas. The key thing to remember here, whether you're writing the equilibrium expression or the reaction quotient, solids, liquids do not enter the equilibrium expression or the quotient. Only gases and aqueous compounds. So only this guy would enter the equilibrium expression. Products on top, H2O. Coefficient is 2 to the power 5, nothing else. That's it. That's the big difference. 15 at on the other hand is we have Br2 becomes Br, both gas. And so QC here would be Br power 2 over Br2 power 1. That's it. Brought to the top reactor. Next. 17 A and D. Let's do D17D. Reaction is SO3 an equivalent to SO2 plus oxygen on gases. You're given all these concentrations. Kp is 16.5 and 111. All of these in 1 atmosphere. And we're asked to calculate the direction of equilibrium shift. Remember, to do that, we compare Q versus K. If Q is to the left of K, Q always wants to become K. If Q is to the left of K, the reaction will go to the right. If Q is more than K, the reaction will go. Let's calculate Q here. SO2 to the power of 2, 2, and SO3 to the power of 2. So that's 1 squared times 1 over 1 cubed. All of these pressures are 1s, that just means 1. 1 is indeed to the left of 16.5. This is K, this is Q, the reactant will move to the right. That's it. Question 25. Calculate the values of Kc to the Kp and vice versa. And each one of these. Remember that the relationship between Kp and Kc is given, right? Question is this. See. Kp equals Kc RT to the power of n. Delta N is the products minus reactants for gas. Gaseous products minus gaseous reactants. 25. Let me do D. H2O liquid, equilibrium H2O gas. We have Kp given, and 2 and 50 degrees Celsius. Don't like that. Kelvin. Let's do something here. 3.5. Excellent. Okay. Take that equation, Ke is 0.122 equals Kc, we know. R. Let's see. We will use the 0.0821 because this chapter has concentrations in it. Concentrations have liters, right? Moles per liters. Liters, we use this lower bound. The power of 10, which is gaseous products minus gaseous reactant. Here, this is a gaseous product, so that's 1 minus, right, because it has a coefficient of 1. The liquid also has a coefficient of 1, but because it's liquid, we don't subtract anything, so the answer is if you were up here, for example, you would say that delta N is 2 plus 1 for the product minus 2 for the reactant. So still comes out. But all the gases, all the gaseous products, and all the gaseous reactants. Skip anything that's solve it for cases by both sides by.
Yeah.
Following reaction occurred with burner on a gas stove is liquid. Methane reacts with oxygen, carbon dioxide, and water is an equilibrium achieved in this condition. No. Chemical equilibrium is achieved in a closed system when the pressure is not changing, when the volume is not changing, when the reactants products are not changing, and so on and so forth. A burning stove is not an example of a closed system, an example of open system where gas is continuously coming out of the stove and is reacting continuously with the oxygen in the air and producing more and more carbon dioxide and H2O gas. Right? So an equilibrium is not established. Because the reactants are constantly being consumed and getting converted into reactants. For 38D, what have we got? How will an increase in temperature affect each of the following? Will it decrease in the volume of the reactant? CO2. Is CaCO3 for the first external T is increased temperature and the second one is decreased temperature increase the increased temperature. Look at delta H, that's negative. The reaction is excellent, which means it releases heat the forward reaction, which means temperature rises in the forward reaction. By extension, that means the temperature decreases in the reverse direction. If your external change is to increase the temperature, the reaction's response will be to decrease the temperature, and it will follow the direction in which temperature is decreased. Direction, which corresponds to the left direction. Similarly, the volumes decrease, the reaction's response will be to the left. Forget about volume, convert it into pressure. Pressure is better. Volume decreases, pressures increase, which means the reaction will respond by decreasing the pressure. Now let's see which side has higher pressure. Count the number of moles of gas outside, just gas. Here is 0, which means this is low pressure, this is high pressure. Which means going to the right reduces pressure, going to the left increases pressure. We want to reduce pressure, so we'll move to the low pressure side. B 52. What is the value of the equilibrium constant? 500 degrees for the moment. And proof is 3H2. And at equilibrium, you're given these 1.35, 1.58. Three uh, 0. This is at equilibrium, so if we calculate the reaction quotient, it's also going to give you K. K is products. 2 efficiency. 2, 1, and H2 1.5. The reason why we're just plugging these values in and not worrying too much about anything else is because the value we're given at equilibrium, which is good. It really has only given the easy questions. No idea why. What is the minimum mass of CaCO2 per cell with an equilibrium temperature? 65 liter container if the equilibrium constant of 50 for the decomposition reaction of CaCO2. Gas, solid, solid. K is given to the Yep. Okay. I see E. Renewable solid don't care, solid don't care. Nothing originally. Plus X. And X. So K is just equal to X, which means that there should be 0.50 molarity of CO2 present in CaCO3. Okay. 0.50 molarity of CO2 comes from. Let's see how many moles of CO2 there would be. Liters, that's the volume given question. It's 5. But that carbon dioxide had come from CaCO3. There should be at least enough CaCO3 to give that much carbon dioxide. 3.25 moles. Cool. Let's convert 3.25 carbon dioxide into information about CaCO3. Take that. Divide by the moles of CO2. Different question in my three. Moles of CO2 cancel. So you get 3.3. Take this, multiply by the molar mass of CO3 and have the grams of CO3. This question is marked in red, but it's a combination of the equilibrium question and a study of where the species of your interest is not exactly included in the equilibrium cell because they're both cyclic dates. But looking at the moles of one of the products equals per minimum amount of reactive structure. I was 81, 82. Equilibrium, this one's easy. H2, gas, CO2, gas, H2O, gas, and gas. 1, 2. H2O is 0.75. CO is 1. And the volume is 5 liters. And the K value is 1.6. What goes into the equilibrium expression are the molarities. So let's convert each of these into molarities. Divide by liters. 1 mole divided by 5 liters is 0.20. It's 0.40. It's, divided by 5 is 15. And 0.20. So these are our initial concentrations. Business as usual, minus X, minus X, plus X, plus X. 20 minus X, 40 minus X, 15 plus X. X. Set up the expression on the top, equations of 1, so 1. 1 equals 1.6. The K value here is done as small. So you can't just small approximation. This is not too bad. This is a quadratic. In fact, it will not even turn out to be a quadratic. Oh, it will. It will turn out to be a quadratic. Simplify. Solve for the quadratic. So they want calculate the number of moles of each component. Okay, so what you're gonna do is you're gonna solve for x. Come back and plug in x here. Once you plug in your x here, you'll get some molarity for this guy, some molarity for this guy, and so on and so forth. But they want moles, so you're gonna take your molarity and you multiply by the liters, convert it back into moles. Right? Each of these answers times 2.5 liters. I'll try and timestamp these important questions in the YouTube video. Okay, done with chapter 13. Chapter 14 is next. The self-ionization of water, endothermic or exothermic, the ionization constant of water is 2.9 to 7.14 at 40 degrees and 9.3 times Kelvin with 1463. Ionization of water is where water breaks up into H plus and OH minus. Breaking up always requires energy. Pretty well. Another way to see this is that look at the K value. It's very small, which means that water doesn't want to break up. If your K value is large, then the reaction is favorable. It wants to happen interreaction. If your K value is really tiny, the reaction is very reluctant, which means that water doesn't really want to ionize. So you have to incentivize it by giving it energy. So it will absorb energy and then break up. That would make it endothermic. Oh, I was doing 14. Whereas what are the hydronium and hydroxide ion concentrations in the solution? This pH is 6.52. This is easy. If pH is 6.52, pOH is 14 minus 6.2. Then 48. And then you tend to the negative 6.2 and negative 7.48 to get your OH minus concentration. Next to 35. What is the ionization constant at 25 degrees Celsius? For the weak acid CH3, NH3. Yeah, conjugate acid to weak base CH3 and NH2. You have KB, they're asking me for KA. That's the question. KA, remember, is 10 to the negative 14 divided by KB. 10 to the negative 14 divided by 4.49. $43 A and D. I think It be easier to find. Yeah, if you have more electronegative atoms, then the acidity can. So if you compare 43A, selenium is not as electronegative as sulfur S, so it's between NaHSO3 and NaHSO4. SO4 has more oxygens, which is also highly negative, highly electronegative, and HSO4 if you have the highest acidity. For basicity, it's the opposite. You want to have low electronegativity. Check the text. 16A. Calculate the concentration of all solid species in Asia as base from AA. Or the question is very simple. They're simply saying, what is the equilibrium concentration of 8ClO and all the broken pieces? 60. Plus minus this is 0. 2 X, so you do square root of that. X equals Ka, but they haven't given me Ka, which is interesting. I guess it's given in some table at the chapter. So just find it, plug it in here, and that gives you your X value. Once you have your X value, you're going to come in and plug all of the information in here. Yeah, that gives you the concentration of all the stuff. To show that the change in the initial concentrations is reflected, you do the 5%. You solve for your X and then you take the initial value of your next. You times it by 100 and make sure that this is less than 5. All right, 60A is done. Moving on to question 70. Determine whether aqueous solutions of the following solvent are acidic, basic, or neutral. So we'll examine each of the ions and see where they came from. Question 17. All of them. So let's do FeCl3. 70. A FeCl3. This is made of Fa3 plus and Cl minus. I sent you. Please check. Yeah, yes, I can do that. Give me, can you put them in the chat, the two examples? Wait, in the meantime, let me finish this question. So this is made of Fe3 plus and Cl minus. Cl minus comes from the acid HCl. Fe3 plus comes from the base FeOH3. HCl is a strong acid. FeOH3, I think, is a weak base. Strong acids conjugate is neutral. And weak bases conjugate is acidic. Overall, this is going to be acidic solution. Acidic salt. So salt is made of two conjugates. If the two pieces are acidic and basic, you don't know what the overall solution would be like. If they're both neutral, then you know that the entire solution is neutral. If one is acidic and one is neutral, then the entire solution is acidic. And lastly, if one is basic and the other is neutral. Okay, here's a question. And question, example 21.2, why don't we convert 0.305 ANU by multiplying this by that, like it is done in example 20.3. Okay, so let's take a look at example 20.2. This is in chapter 20. Oh, nuclear chem. I see. I have two more questions in this chapter, and then let me move on to nuclear. 80. Okay. So I've got C2, CO2H. Let's say H2O. H3 plus. CH3, CO2. Ka 1.8 times equals liquid. And we're given that the acid is 0.25 here, and you're also given that the concentration of NaCH3CO2 is 0.0. NaCH3CO2 This breaks up into Na plus and CH3CO2 minus. That's the information that we care about. You have a mixture of a weak acid and its conjugate. This is a buffer question. Henderson Hasselbalch. To calculate pH, pH equals pKa plus log concentration of conjugate 0.030 divided by concentration of the acid 5. Plug in your pKa, solve the pH, but they want the hydronium concentration. So at the end, do 10 to the negative pH. Calculate your H plus 5. Last question of this chapter is question 94. Okay. Barbituric acid. All that HA. I don't know what the chemical form of barbituric is. It's actually the HA reacts with strong KOH. And we know what happens with the react. You can have some water from HAA minus remains and KOH minus remains. Initially you have 40 milliliters, 0.1 acid, which is 4 millimoles. Barbituric acid. And in the first thing, what you want to do is no KOH is added. So you can basically forget about this. Let's forget about this for sure. So nothing is added. This is 0 and 0. Let's forget about it. It's just the regular minus X plus X plus X. And in fact, since no KOH is added, we can go back to using molarities actually. This was 0.1. 0 and 0 minus X plus X plus X. 0.1 minus X X. X squared over 0.1 minus X is the Ka is given to be 9.8 times 10 to the negative 5. Smallest approximation, solve for X, you're done. This is part A. Part B is where KOH is actually added. So now we're going to resort to doing millimoles because now it's a titration question. First part was not a titration question. Was it 4 millimoles that we calculated up here? 0. Oh, actually, don't care. 0 and 0. How much KOH was added? 20 milliliters. KOH is also 0.1 mole. So that is 2 millimoles. Minus X plus X. In fact, this is a big ice table because it's a titrating ice table. The reaction goes to completion. So subtract away the lower amount. You get 2, 0, 2, and 2. What you end up with a mixture of the weak stuff with the conjugates of the buffer question. Anderson-Hasselbalch is pKa plus log concentration of A minus 2 over concentration of HA, which is also 2. 2 over 2 is 1, log of 1 is 0, so the pH here is just pK. Let's take a look at C. Four, which is added this time. 39 milliliters is added, so that's 3.9 millimoles. Multiplied by 0.1 molars. Minus 3.9, plus 3.9, plus 3.9, and so you got 3.9 and 0.1. Anderson-Hasselbalch again. It's also a buffer question. Part D, on the other hand, should be different. Or this time we have 40. So also 0, 0, and 0, don't care. Minus 4, minus 4, minus 4, minus 4, 0, 0, 4, and 4 millimoles. Okay. Let me quickly divide 4 millimoles with the total amount, the total volume, which was 80, 40 from the acid or base. That gives you 0.05. And so all that survives at the end that is active is the conjugate. So let's write down the reactor for the conjugate. Reacts with water. Gives HA, OH minus. Oh, this is 0.05. Don't care. 0.0. 0.05 minus that. That equals KB because there's OH minus here. And so you take the Ka, convert it to KB, solve for X. It should still work out to be a Smolensk approximation. Last part is 41 milliliters of KOH. Let's do that. But this basically covers all three cases of titration. 4, 4.1, 0, 0, here, minus 4, plus 0.1, 4, 4. This time, the strong you can provide at the end. So we remember everything else. Just look at the strong. KOH completely breaks down into K plus and OH minus. We get OH minus concentration is 0.1. That would give you your KOH. Which actually comes out to 1. And so your pH is 14. Popular demand. So I take a look at chapter 21 questions. Regarding, let's see, 21.2. Calculate the nuclear binding energy. Okay. Binding energy for the nuclear He2O4 in joules per mole and nucleus. Okay, electron volts. So what is the problem you want to? Also, I can't hear you. You'll have to put your messages in the chat. Wait, how long have I not been sharing the screen for? Let me get back to you on that question. And not exactly sure about this. Okay. One thing that I forgot when I was going over nuclear chemistry with you guys is the binding energy. Slipped my mind. In any nuclear reactions, if you calculate the total mass of the reactants and the total mass of the products, there will be a slight difference. Let's call that difference delta. To find the binding energy, you take that delta N and plug it into E equals x+. The delta N goes with that. But the delta N must be in kilograms. C is the speed of light. Gives you the binding energy. Once you find the binding energy in joules, so this gives you the answer in joules, you can convert it into mega electron volts, or you can convert it into joule per mole by dividing by the total number of moles of your nuclei for which you calculated the mass defect. Or you can do mega electron volts per mole by dividing by the moles of, wait, once again, the moles of your nucleates. So that's all there is to it. Let me see. Take a look at these nuclear chemistry questions. See if I can find something like that. The nuclear chem is easy, it's fresh in your mind. I'm not going to go over these questions with you. 313. It's easy. 15. That. 7. A little handy rule for this. Half-life is the amount of time it takes for your sample to reduce to half its initial size or initial number. And so, for example, if the half-life is 5 years and you start with 100 nuclei, 5 years later you only have 50 left. 5 years from then you have 25 years left, and so on and so forth. Is approximately let me come up with an explanation better. I'll put that in. We've done a exact same in class, 39. I'll do 30. Sample of rock was found to contain 23 milligrams of radium-87 and 147. Oh, okay, this is good. Radiodating. Eight point 23. Radium-87 and 147. I think rubidium decays into strontium. That's what it is. Yep. Half-life, the decay of rubidium by beta emission, half-life is given to 4.7. It's 10 to the 10. And we will calculate the age of the rock. Okay, cool. This information is about rubidium. So our entire focus is going to be on rubidium. This is there for a secondary purpose. Right now, you have 8.23 milligrams, which means initially it was a little more because over time it decayed. How much more? Well, all of the strontium that formed had formed from rubidium. So this 0.47 came from the rubidium. So the initial amount is 8.23 plus 0.47. That's how much in the beginning there was rubidium, no strontium. Over a length of time, some of the rubidium got converted into strontium. So basically factored. So if you add these up, 8.23 plus 7, that gives you 8.7. This was the initial. Remember, nuclear decay is first order, so RB for initial equals minus KT. So ln of 8.23 now versus what it was equals e to the minus k ln2 divided by half-life times t, and you're trying to solve for this t. Oh no, it's just minus k. Minus ln2 divided by 4.7 times 10 to the 10 times t. You're just trying to solve for t, so multiply both sides by this guy. That's how you do radio dating questions. All right. Electrochem. 16 is thermal. Is electrochem. Three A. This releases one electron, this releases two electrons, make the electrons equal, don't multiply two equations, and then add them up together. It's like balancing half reactions. 9. Why don't hydrogen ions appear in equations for half reactions occurring in basic solution? Because they all get consumed by the OH minus in basic solutions and get turned into water. They get neutralized. Cell schematics. So very simple. Okay, like for example, Mg plus Mi2 plus. Is Mg2 plus. Ni. Look, magnesium is becoming Mg2 plus. Nickel 2 plus is becoming Ni. Magnesium to oxidation. So this is what a cell schematic looks like. Oxidation on the left. Reduction on the right. And mention their states. That's the cell schematic. Mg becomes Mg2 plus, single line between them, and then between oxidation and reduction, you also have a double line. Calculate the standard cell potentials. Look, magnesium is involved in oxidation, nickel is involved in reduction. It's reduction minus oxidation. And when you're looking for your oxidation equation in the table, you have to flip it first. That's easy. We've done that. 25. Determine the cell reaction and standard cell potential at 25 degrees, but still you got anode, acid, cadmium electrode, blah blah blah. Standard conditions. So you've got two buckets. One has cadmium in it, one has aluminum in it. So what you'll do is first to figure out which one's involved in reduction and which one's involved in oxidation. You'll go and look at their standard reduction.
Yeah, I actually decided to.
Let me pull up. Standard reduction. We're looking at cadmium, CD. Yeah, cadmium's over here, and aluminum, which is down here. Cadmium is higher in the table compared to aluminum, which means cadmium is better at reduction than aluminum. So cadmium is going to be the one that is reduced. Aluminum is going to be the one that is oxidized. Oxidation happens at anode, so aluminum better be at anode for this cell T1. Is it the case? Aluminum should be on the anode. See if that is the case. Nope, the reaction is not spontaneous because the anode has cadmium on it. It should have aluminum. So that's how the higher the value of reduction potential, the higher one wins at reduction. That's the idea.
Formula. Also, look. These books.
5. Yeah, that was. plugin chart. There is a delta G. Um, for each pair of standard cell potential and electron stoichiometry values below calculating corresponding, right? E0 cell is minus RT over NF times ln of what is it again? Delta G equals minus RT over NF. Delta G equals minus RT ln K. And also E0 cell is minus RT over NF ln K. You want to calculate G, you have E0, you're not interested in K. Let's divide both of these. The ln K's go away. RT's go away. That's the delta G over E0 cell. If I'm doing this correctly, it's going to be NF, which means delta G is going to be NF E cell. Plug it. You're given E cell in each case, and the N value in each case is 96,500. And I want to end with this chapter. 31. Once again, same thing. E0 cell equals minus RT ln K. You're solving for K here. And you can calculate the E0 cell by looking at the values in appendix L right here. It's, all right, that should be good. We covered a lot of questions. Should be set. Of course, if you have any last minute questions on a specific topic, reach out to me via email and I'll get back to you. All right. Good luck.